Hello, everyone who's here for the first time in this stage, on the beta stage. Anyone? No, everybody's been here. Good. An only person raised the hand and so shyly, like, hello, I'm here for the first time. Anyway, I am excited because we're gonna have a very fun presentation. David, you can come on here. Yeah, you can. Is your microphone working? Do you have it?
Tech. Check. 1, 2, 1, 2, 1, 2.
Do we hear him? Because I don't hear him.
1, 2. 1, 2. 1, 2.
Where is it?
1, 2. It's hidden. It's camouflaged.
It should be so much closer.
It's camouflaged.
Don't
Here we
camouflage
go.
it.
Let's do it.
Yes, it's
There
that
we
kind
go.
of microphone.
No,
It has to be
almost.
on your tongue.
On my lips.
Yeah. So now we hear
There
you,
we go.
thank
1,
God.
2. 1,
So,
2.
David Whitney, hello. And the audience is not like in the, you know, concerts or entertaining events or whatever, because when I say David Whitney, hello, you should clap and scream.
There we go. We got it.
Sometimes I feel like they never leave their offices or whatsoever, because this is a normal practice. If I do this, you do this,
You scream.
and stuff like that. Okay, I will not repeat that. I will not torture you. So, which was the first time you were in Bilstead? Because I see you every year.
I think it was 2015.
2015, which is...
I'm old. I don't
Well, like, you are older than me to this event. I'm here for 5 years only. And every single time you talk about 3D rendering or...
just the same talk again and again. It's not. This is talk 2 of 4 this week. which is
First talk,
terrifying. Yeah, I'm an idiot.
How do you say that in English? Fourth?
4, 4.
Number 4,
Yeah.
speech this week.
This is number 2 of 4.
Okay, okay, so you're
So
a
if you
busy
don't
boy.
like this one, probably skip on the other ones with my name against them, right? That's the thing.
But
You
only
get to
this
try
week.
before you buy.
Only this week. Okay, so we're gonna talk about rendering 3D worlds in where? Where can we see that? Where can we use that?
We can use it in C#, but actually it's a big old fake out, because what we're really going to talk about is perspective and classical art. Yeah? Bet you didn't expect that.
Okay, David Whitney, take the stage. I'm just gonna leave. This is gonna be very interesting.
Let's do it. Okay, so if you have... Are there any game developers in the room? Thank God. Studying game development, please don't ask me any questions about it afterwards. I jest. If you ask me about maths, I'm not going to do very well. But this is a talk about maths, but it's more a talk about arts. Let's keep this really on my face. I'll refer you to Wikipedia. So I'll introduce myself. So my name is David, and I am a head of architecture for a boring finance company in the UK. And in a previous life, I was a software consultant for about a decade, and I like programming. And I've had loads of weird job titles, but what I really like to do is write code and play with people that like writing code to do stupid stuff, because everything doesn't have to be work, right? And everything really doesn't have to be work. I wrote a couple of kids' books about programming in JavaScript that you can buy. And recently, I built a 3D renderer from first principles to see if I could, I guess is the real answer, just to see if I could do it. Literally, why on earth would you do that? There are already 3D renderers out there. It's all a bit pointless, but that's the point, really. That's the fun. There are lots of different answers to the question, why. So often we're forced to live in this brutalist, capitalist hellhole where only things that have to exist for money get made. And I hate that. I think it's awful. So I like doing the opposite things. 3D engines exist. If you want to build a game, don't build it in my own 3D engine. That's a really stupid idea. Go use Unity, go use Unreal Engine. It's fine, your game will be awesome. But if you want to do silly things to see if you can, to see what you're capable of, we're going to go on this journey, because I'm not a graphics programmer and I'm not a mathematician. I'm terrible at maths. So I was coming to this a bit cold. But before we get going, I want to caveat through a few things about sequencing and history. So in this talk, we're going to talk about a lot of technological advancements, ranging from kind of the 70s through to the mid-2010s. I'm going to be talking about things that have come after each other in various orders. For every game I mention, there were other games doing the same things at the same time. So if I miss your favorite game, don't come and try and set me on fire at the end, please. I'm sure your favorite game is awesome. So before we do a deep dive into code, and there is code in this, I think it's important to understand what three-dimensional images really are, what 3D means. Now, your computer monitors are two-dimensional, I hope, probably. They literally have two axes, an x-axis and a y-axis, cross and up. And when you try and draw by hand something that looks 3D into a 2D space, it often looks strange and wrong. So the screenshot here is from a game called Rampage. So that's in 2D, but it's clearly representing a three-dimensional space. But it's definitely not a 3D image, it's a two-dimensional image. It's not even pseudo 3D because there are two planes. Now, there's literally just left and right and up and down in this image. Now, excuse me, making a two-dimensional image three-dimensional is not about the fidelity of the image, and people often think that 3D is about fidelity of graphics, but it's in fact about how the image captures perspective. Right, so perspective is actually a technique from classical art. Did anyone study art? Have we got any artists in the room? Thank you. Please don't judge me if I get any of this wrong as well. So perspective is a technique from classical art for creating the illusion of 3D in a two-dimensional space. And the correct use of perspective was one of the great inventions of the 15th century, right? And there's a turning point in classical art where people worked out how to do perspective. It's often credited to Leon Battista Alberti in a book called On Painting, which came out in 1435, so probably not in your local library now. Linear perspective is just one kind of projection technique. Now, a projection is a graphical technique that maps three-dimensional points into two-dimensional space. Right? It's an engineering and fine art discipline, so building projections for architecture use projections. And it can be learnt because it's mostly maths, actually. It's not like a creative process, it's a mathematical thing. And projections come in many forms, mostly defined by where their focal points are placed. So these are all different projections of a three-dimensional object into two-dimensional space, because this screen is flat, right? There's nothing 3D about this. And accurate perspective projections, it's a bit of a tongue twister, are what makes something look 3D. So, one-point perspective is the most popular form of perspective that you will see, especially in games. You will see it in first-person shooters, anything where the camera is where someone's face is. Now, it's normally from the focal point of a character, but over time, games have used lots and lots of other kinds of perspectives and projection techniques for different kinds of pseudo-3D. Now, early games often favoured what we called orthographic perspective, so isometric rendering of 3D worlds. So it's kind of a lie when people think that 3D graphics were invented in the mid-90s, because people have been doing 3D projections since the 70s. Like, we still consider them 2D games because the running model of the game is not three-dimensional, but they were technically representing three-dimensional space. Now, isometric perspective is useful for games because all the objects inside the 3D space remain the same size. So the reason it was one of the earliest forms of 3D in games is because you didn't need to do scaling and rotation, which were computationally very, very expensive until like the mid-90s. Now, it's worth remembering that when we talk about three-dimensional games today, what we're really referring to is polygonal 3D. I mean, I'm sure someone could put their hands up and say, what about voxels and other kind of representations of 3D, but generally polygons. And gaming has a history of pre-polygonal 3D graphics that's actually kind of worth considering, because there was a journey that took us to this place of high-performance polygonal 3D. So, this is a screenshot from the very recent Unreal Engine 5 demo that everyone collectively lost their minds about. You really have to marvel in the absolute beauty of the detail in this thing. Like, it's unreal. They don't pay me for that. There are literally billions of polygons in this image. Millions of polygons on every single rock, each decorated with 4K scan textures that they took from photogrammetry. There's global illumination to do real-time shadows, there's depth of field, there's particle effects, there's material simulation. All of this is implemented in what they call pixel shaders. And they basically run on specialist GPU cores that crunch pixel data in real time. Like, modern 3D is this accumulation of 3 decades worth of research, is the truth. But to really appreciate modern 3D, we're going to take a look at the road traveled and some of the really interesting proto 3D that you might remember from looking around at the age of people. You might not remember from being kids, but I do. So on the left we have Tempest here, and on the right we have Maze War. Now, long before general purpose 3D, back in the 70s, we had what appeared to be 3D graphics and vector-based games. So these were line drawing exercises where someone just was really smart and did the maths, right, to work out how to do this. So if we look at the screenshot of Maze War here, so this is a 3D first-person shooter written in 1973, running on a PDS-1 mainframe computer. Yeah, I don't know how people ever work this stuff out. So it was made up of what appeared to be empty hollow polygons, but it's actually something very different. There are no pixels at all in that screen because it's a raster display. So the polygons didn't exist in the game code. They were line drawings on vector monitors. So vector monitors were not divided into pixels like a modern display is, but instead they're basically the displays from oscilloscopes. There we go, got it in two. So this was a trend that actually continued into the early 80s and early arcade games, so even Star Wars got in on this. So the surface of the vector display screen is a single layer of phosphor, and it emits light wherever the electron gun hits it, much like early CRT TVs. So it meant that if programmers were creative enough, they could manually, in their code, instruct the display to draw whatever shapes they wanted in a point-to-point way. It's kind of like tracing lines. So games like Tempest and Asteroid and the early Star Wars arcade game, and consoles like the Vectrex. I don't know if anyone has heard of the Vectrex. So really interestingly, as an aside, the Vectrex was a console that was created because someone that sold surgical implements realized they had a surplus one year of their vector displays. So they built a games console to flush through the spare screens, which is why it's now a really rare collector's object, because they didn't have much stock. So they made an entire console just because they had spare hardware. It's weird. It's a company called Smith Engineering. Pretty cool story. And these were all basically oscilloscopes, glorified oscilloscopes. So then we get forward to kind of the 70s and 80s, and things start to change here. There was a broad shift towards raster graphic displays, and raster graphic displays are displays that have pixels, basically, that you can address by pixel. Now, when compared to a vector display where you could literally draw anything anywhere, raster displays use bitmap graphics to map to those pixels on the screen. What that means is the pixels would directly map to an area in memory that clever programmers could poke bits into to light up different parts of the display. You've all used them, you're still using them today. Your phone screens are raster displays, they're just very high resolution. Now they provide a level of hardware abstraction over low-level drawing operations that vector displays didn't have. So all of a sudden, kind of doing high-fidelity graphics became more approachable to the average programmer. And it's like anything else in software, as the level of abstraction rises, more people get to experiment with a piece of technology. So that was pretty cool. And you know, raster displays actually weren't new when they became popular. They date all the way back to Pong. Pong was done on a raster display in 1972. And but over time, the use of vector displays became less and less common because raster displays became more popular. There was just occasionally a notable exception, like the Star Wars game, and the last slide actually came out after the popularization of raster displays, because they realized they could simulate 3D by doing that thing. Now, the games of the 80s that featured 3D often used artistic technique to simulate 3D, which was really just raster graphics approaches to the earlier line drawing 3D techniques that they had in vector displays, just with higher fidelity and better colors. So occasionally, in the case of Atari's iRobot in the top left here, specialized hardware was actually built into the arcade cabinets to do specific polygon drawing techniques over the flat images. So in this case, literally this game had a custom 3D coprocessor to do that depth of field thing. It's pretty cool. So, and then we get to basically my childhood and what Sega called their super scalar architecture. Because Sega always named things like that, right? They had blast processing, which didn't exist. It's great. It was a marketing term that they used to say they were better than Nintendo, but it was just a complete fabrication. There was no blast processor. Very good. Only in the 90s. So they had a bunch of arcade boards that powered games like Space Harrier and Outrun and the other one, Afterburner. There we go. And Sega had become really adept at sprite-based pixel art in their home console work, so they built specific hardware to do scaling and rotation for these big, expensive arcade cabinets. This kind of fast sprite scaling was way beyond the capabilities of consoles of the 80s because the processors weren't fast enough to churn through the pixels. So they introduced Superscaler in 1985, and the guy that did it, a quote here that I'm going to have to read, so Yu Suzuki was quoted as saying that the Superscaler games were designed as 3D games, then simulated using sprite scaling to look like texture-mapped 3D, while looking more impressive than early 3D polygon graphics because we didn't have the processing power to fill in the polygons. So actually, for a while in the 80s and early 90s, this kind of weird sprite-scaled 3D looked a lot better than what we had in polygonal 3D. And in fact, the Superscaler technology was similar to the really hyped Mode 7 graphics mode of the Super Nintendo. I don't know if anyone remembers that. All Mode 7 was, and they used to use that on box advertisements as well, which is really weird when you think that the thing that they were advertising was a graphics display mode that you set by flipping a register on the CPU of the SNES processor, and that's what they used on the front of the box art, like Mode 7. Cool. So what that did is it included hardware support for scaling and rotation, obviously made very, very famous by F-Zero and Super Mario Kart originally, because all Super Mario Kart's levels are flat bitmaps, stretched and skewed and rotated, with a bitmapped image in the middle for your driver, and they just move the map underneath you. It's great that you can build that in CSS in a browser now, in like 3 lines of code. It's amazing. So here's an interesting other one. This is great. This is Tomb Raider. So Sega was so good at rotating bitmaps that it formed the foundation of the Sega Saturn's 3D processing engine. So the Sega Saturn was notoriously very, very bad at 3D. And it's basically why the PlayStation eventually won the console wars of the 90s. Is because Sega's implementation of 3D was, you basically get a lot of bitmaps, and you staple them together, and you skew them over the model of the polygon to try and make it kind of fit, and it was really weird. So Digital Foundry, I don't know if you've ever heard of them, they're a really great kind of YouTube channel that are owned by Eurogamer. I think they do teardowns of game engine tech. Did a retrospective on Tomb Raider where they got a Saturn emulator and they disabled the part of the processor that did the hardware stretching and skewing, and that's what Tomb Raider's 3D looks like when you disable that little bit of the Saturn processor. So kind of cool. Ironically, it gave Saturn the reputation of being hard to program for, and pretty much probably killed Sega. But they brought a new Sonic game out yesterday, which is apparently very good. Should be a first in 20 years. So now we get to the 90s and the good stuff that people like. This is what games look like today, right? This is what you all play. So in the early 90s, there was this slow, lumbering lurch towards 3D. And like early 3D implementations were really, really, really rough. And all the way until like the mid-90s, 3D was like ridiculously low polygon. Now you can probably count the polygons from where you're sitting now in some of these characters in Virtua Fighter, the Lego bricks. And the engines were slow, and what it did is it constrained the art style available in games. So we kind of came from this place of really expressive 3D craftsmanship using 2D sprites to basically some boxes stacked together for about 3 years. This stuff was really aged badly. I have a certain nostalgia for this, just because, like, I don't know, I'm 38 years old, I was 11 when all this stuff came out, and it was like, oh my god, I can't imagine graphics will ever look more realistic than Virtua Fighter. Yeah. So, given the relative quality of 3D at the time, in the early 90s, you can perhaps understand what Sega was thinking when they went with their pixel art skewing approach. And in fact, Sega themselves took their first stab at true 3D with Virtua Racing all the way back in August of 1992. Now, it was initially a proof of concept application for creating a 3D graphics co-processor for their, what do they call it? Their Model 1 arcade boards, that was the thing. So the late 80s had seen some polygonal titles, but by the time the Model 1 and the Model 2 arcade boards came out in like 93, 94, you kind of got Sega's huge hits and the start of modern 3D. Now, while there were plenty of games reaching for real 3D at the time, it was probably a mixture of Mario 64 in September 1996, down here. Probably everyone has played Mario 64, it's like the one timeless early 3D game. Tomb Raider, which was October 96, that really solidified, and Quake in June 96, right? So these were the three games that really made 3D viable for most people, and they were most people's first real 3D. So the Saturn had shipped home ports of Virtua Racing and Virtua Fighter in late 94 as well, but those games became very, very dated very, very quickly. So by the time the PlayStation and the N64 launched in 1995 and 1996 in the West, like, 3D games were mainstream. Now, there were plenty of other games doing 3D between 94 and 96. Like, it's easy to remember just how ropey some of the game design was at the time. And the truth is, it was almost entirely new territory. Nobody even knew how to do control schemes. And if you actually go back and play some of those early PlayStation 3D games, there's all sorts of tank controls and shoulder button rotation and just like weird stuff as people were working all this stuff out. Of these three games, Tomb Raider has probably aged the worst. And you can tell because they've remade it twice since to try and cover over that. They had really unfortunate control schemes, like original Lara Croft did control like a tank. And it was all very, very grid-based, and all the jumps had to be very, very precise. It basically isn't very fun. Quake basically still holds up, and every 3D shooter that you ever play is still more or less Quake with a texture pack today, and a lot of texture packs. So a little bit of a quick recap before we go on, because that was a lot of novel history. We've kind of talked about three ways of simulating 3D through early video games. We talked about vector line drawing projected into 3D. We talked about early orthographic projections to render isometric viewpoints from fixed size sprites. And we talked about sprite scaling and rotation to simulate 3D models. And then finally, the old polygons that we still have today. But we've not talked much about speed, and we've not talked much about the home computer market, which is a very, very different beast from the arcades. Now, there was this kind of parallel thread in PC gaming in the 90s, and the PC existed in this kind of alternate universe where, from games development consoles, and the conventional wisdom was that PCs were not as fast as games consoles, which is quite ironic by modern standards, where the opposite is held true. So the IBM PC standardized hardware in the early 80s, but it wasn't really seen as a thing of play. It was for offices, it was for work, it was stuffy. And we were still basically at the tail end of the 80s microcomputing trend, with things like the Amiga and the Atari kind of still pulling up the back. That's not to say there weren't games on the PC in the 80s that were 3D, but the kind of games were often slow and laborious. So you had like text adventures, which were all 2D projections of 3D. You had things like the Ultima Online series, which were almost like a frame by frame, 1 frame a second as you pressed a keyboard, dungeon crawling navigation game. And it was all a bit slow, but not graphically rich, not fast paced, not games like Mario and Sonic, which is what all the kids wanted to play. People thought PCs couldn't do it. So let me tell you about the game that is secretly really, really important. This thing, really, really weird. So this is a game called Hover Tank 3D by Softdisk. Now, in 1991, a company called Softdisk put out this game as part of their Gamer's Edge series of monthly discs, and it was literally a magazine subscription with a floppy disk on the front. And Softdisk had made a name for themselves as part of the burgeoning shareware scene that was one of the, like a couple of game studios out there. So it described Hover Tank as this. Hover Tank 3D is set during a nuclear war, of course it is. The player controls Brick Sledge, a mercenary hired by an unknown organization, referred by the game as the UFA, to rescue people from cities under the threat of nuclear attack, largely political activists or scientists, both by the government and large corporations. However, the cities are also full of mutated humans, strange creatures, armed guards, and enemy hover tanks, because of course that's what was happening in that game. So Hover Tank 3D was actually secretly really important, and it was really important because of these guys. These guys. I bet they hate the fact that they ever posed for this photo. Like, it's absolutely brilliant. Does anyone know who they are? Anyone? A couple of people. I see a few hands. Okay. So the 4 people that were working at Gamer's Edge were John Carmack, John Romero, Adrian Carmack, and Tom Hall. So those were the people that would go on to be the 4 founders of the studio id Software. And id Software, that in these wonderful 90s photos, I like the romance in this one. I love it. So in their evenings, while they were working at Softdisk, what they were doing is they were literally putting their work computers into their cars and taking them home at the weekends to work on 3D games. And those games would later be the id games. Now, the really interesting thing about it, you seen this game before? You probably haven't. That isn't Super Mario Bros. 3. So what that is a hand pixel drawn clone of Super Mario Bros. 3 that id Software built in, what year? 1992. So they were trying to get the license from Nintendo to port Mario to the PC, and they basically built a smooth scrolling 2D platform engine that was as fast as the Nintendo Entertainment System. So that is not a screenshot of Mario 3. They got a video recording of them playing it and were freeze framing it and tracing the pixels from the TV screen and replicating it in their game engine. It's pretty, I kind of love it. Now, that led to them building and releasing Commander Keen because Nintendo told them to fuck off. Basically said, look, that's copyright infringement. You can't do that. Leave Mario alone. We want to sell Nintendos. So they made Commander Keen, which was a 2D side-scrolling platformer in a blocky world with a small character that could get bigger and had a few... Yeah, it was Mario. It's just a Mario game on the PC. So in another world, Super Mario Bros. 3 might have been released on the PC and we may have never played Doom. Right? That could have really happened. So Hover Tank 3D was the game that they built after Commander Keen, and it was their first 3D engine. It took 6 weeks to build compared to other pseudo 3D engines at the time. It was really fast, right? Hover Tank 3D was fast, and Doom was faster. So it's pretty gory, isn't it? It was the game engine that formed the prototype of the Wolfenstein 3D game engine, which would later become the foundation of the engine for Doom. Id would go on to develop Quake and its various sequels. They built Rage, a bunch more Doom games. They're still making games today. John Carmack was eventually the CTO of Oculus. Competed with Elon Musk in the amateur rocketry race as well, weirdly, with a company called Armadillo Aerospace, and is now terrifyingly working on general purpose AI. And when most people tell me they're working on general purpose AI, I think it's a joke. When I hear that John Carmack is working on general purpose AI, I'm terrified for all of humanity, I think is the truth. So these games were very, very famous because they were fast, right? They were really, really fast, and that's what made them playable, and that's what made them addictive. Now, along with pioneering, they also invented online multiplayer, just on the way, casually. You know, when people are just such overachievers, you feel thoroughly inadequate with your entire career? Those guys. So Doom used this technique called binary space partitioning, and it used it for rendering, and we're not going to deep dive into BSP here because that was their leap between Wolfenstein 3D and Doom. And we're going to go back to Wolfenstein 3D and how its renderer works. So if you're interested in more history on kind of the story of id Software, this is a pretty entertaining book. It's one of the few serialized books of like 80s computer programming that isn't completely rubbish and awkward. It's a bit dramatized, but it's a fun read. So there are only 2 things you need to know about making things run fast in 3D. Render as little as possible, and do maths really, really quickly. Right? That's basically how 3D works. I half joke, but it is as true now as it was in 1991. The games industry today is basically full of clever optimization techniques to work out how to render the absolute least things possible, and we build special hardware to do the maths really fast. What we're going to do is we're going to look at a technique called ray tracing, which you will probably heard of from current generation graphics. It was the basis of the rendering engine in Hover Tank 3D and Wolfenstein 3D, and it was really an early approach to trying to make things run fast. Now, we're going to talk about raycasting and the difference between raycasting and ray tracing. So, raycasting is, I have to read this as well, the use of ray surface intersection tests, write that down, to solve a variety of problems in 3D computer graphics and computational geometry. The term was first used in computer graphics in a 1982 paper by Scott Roth to describe a method for rendering constructive solid geometry models. Thanks, Wikipedia. So, Wolfenstein 3D uses raycasting to convert a 2D level design. So this is a Wolfenstein 3D level. This is actually the level data. That's what it looks like. And it converts that flat maze into a 3D projection, which is exactly what I was talking about at the very start of this talk, where you have to project a two-dimensional space into 3 dimensions with a rendering technique. So we're going to dissect and then clone this behavior. So how would we convert that map, which is a 3D map, into a 3D world? Well, I've drawn a really crude map here on this slide. It's the best level design I ever did. I will accept my BAFTA. Towards the bottom of the map, I've drawn a circle, and that circle represents our camera facing north. Now, if we were to imagine the camera was casting rays, we would draw straight lines for every pixel in its field of view, one by one by one by one, like this, that look more or less like those lines drawing from the camera point there. Now, the number of rays we're casting here isn't that important, but in a real-world example, it would be related to the focal length of the camera. Now, the further a ray has to travel from the origin before it makes contact with something, the further away that thing is. So you are literally counting. We've got 8 rays in this example. Now, imagine that we record the distance that each of our rays travel, and we fill up some columns. So the further a ray travels, the fewer pixels we fill up in the column. Now, our first ray was really close to this left-hand block. Oh, it's up in the corner there. The second ray is clipping the edge of it, so we fill up quite a few, but less than the first. And then the third and through the 6 are shooting way off into the distance, so we fill up only a few pixels. And then once we reach our 7th and 8th rays, we're connecting with the right-hand block, so we're filling up more again. So when represented like this, it doesn't look much like 3D, but the magic trick, if I center the blocks, it does. That's raycasting. So if we center them and we make sure the same amount of space is equally divided between the floor and the ceiling, suddenly we've got a 3D world. Totally works, and that's how Wolfenstein 3D did it. So we've got a wall in the far distance, we've got some blocks on our left and right. Fundamentally, you shoot a number of rays, you scan across the distance before they travel to connect with the surface, and if the surface is solid, the ray stops. That's all we do. If the surface isn't, we continue onwards. Now, this approach is faster than any other rendering technique that orders objects. So another popular 3D rendering technique is you try and render everything and you cull the things that you can't see. And that was a lot more computationally expensive with these early 2D maps than just counting. It requires multiple passes sometimes to get a really great image, but it's beautiful. And now the interesting thing is there's a whole bunch of graphics techniques today in modern ray tracing graphics cards that use these exact techniques. So a lot of NVIDIA's cards in the last 5 years have had ray tracing cores. That's why they've got RT written in their product numbers. And what they do is they do limited ray tracing to measure the bounced light distance off surfaces. So instead of their rays just stopping, they bounce them and sample the colors of objects they hit. And then they upscale that with AI and they apply it over a rendered image to make the image look better. But it's still the same stuff. Now, what we do is, to build this, we need to set a max range on our camera, otherwise we shoot rays off forever and our computer crashes. So our rays simply give up if they don't make contact with anything off into the far distance. And if you remember Nintendo 64 games and the way that they used to put fog over everything, that was when they stopped actually casting rays in those early 3D engines. So we can express the number of pixels in any given column as a percentage of the total distance. So we calculate the percent of vertical pixels that fill up any column as the distance traveled is then divided by the camera range times 100, right, to give us a nice little number. By doing this calculation, we've got a measurement. That's the height of the blocks we have to draw on the screen, and what we're doing is we're projecting 2D into 3D. And that's basically what it looks like when we do that for every pixel across the horizontal resolution of our screen. So we've looked at how we can use raycasting to determine the difference between an arbitrary camera and surfaces in a 2D space. But how do we practically turn this into an image? Well, the simplest way possible is we just cast all those rays for each pixel. And while we're only considering 8 in our example, this could just be 1024 by 768, right? Or a HD resolution. Actually, 1920 by 1080, so full HD, is totally doable in this technique using modern computers, because modern computers are so fast but it doesn't really matter. So let's build our own 3D engine. Let's do it. Now we get the theory. So of course this is kind of a .NET conference, kind of. Not a history of video games session, even though I've kind of tricked you to tell you the history of video games on the way. What we're going to do is we're going to define our own map format and write the simplest raycaster we possibly can. And we're going to do a little bit of scary looking maths, and I said at the start I'm not a maths person, I just had to look it up when I was doing this. And we'll render our own 3D world. So look at this, my finest 3D game level. Perfect. 2 cubes in a room, be astounded, be amazed. I can just feel the cover shooter gameplay, right? This is just a file, it's a bog standard file, new project, default .NET console app as of, I suppose, Netcore 3.1. And it's a string array of spaces and hashes. So it's an innovative new storage format called hashes for walls. BSP got nothing on me. So for the scale of this example, any space has a height of 0, and any wall has a height of 1. Now we're just setting a camera as a location 2D. Down here it's really by the floor, and we're giving it an X and Y coordinate, which will just basically pretend there's a camera in that map. And it's 10 characters down and 7 characters across in the array, and it's facing to the right by default. Now our array is a list of sample points. A sample point has a location that it's currently sampling, along with storing the length of this part of the array and the total distance traveled. Now the idea is that as we write code to walk through our map, we'll just append a sampling point to each array, and a collection of sample points is a array, and the number of items in that collection is the distance traveled. So the final sample point that connects with the surface will always be the last sample point in the array, and you'll notice we have a property in the sample point called surface. Now on our map we only have 2 kinds of surfaces, a wall and space. But if you wanted to say do texturing or have different half height walls or windows or glass, you could return a different surface that array makes contact with later on. Now, I'm probably standing in the way of the code. There's a lot going on here, so I'm kind of going to read through it slowly. We're going to create a new result, which is an array of sample points, exactly the width of our desired image. Now remember, each horizontal pixel needs a sample point, needs a raycasting. Now we're then going to do a for loop for each pixel in our target horizontal resolution and shoot a ray. Now we work out our x value, the angle of the ray that we want to cast, by taking our column number, our pixel number on our horizontal resolution, and then dividing it by the render width and subtracting a half to make everything a little bit squished. This effectively takes our desired camera angle and splits it into columns, and then positions our camera in the center of the array of text. We create an origin sample point at the location of our camera, and then we're going to work out which direction to cast our rays. Now this is one of those maths things that if you weren't paying attention to in school, you will never use in your life until you try to write a 3D game engine, and then you have to use it. Actually, there's a game out on the floor from one of the vendors which has all these weird maths questions in, and I tried to do it before and failed spectacularly. So a radian is a standard unit of angular measure. It's a great sentence. It describes how many degrees around a circle that you are. So the direction in degrees that we want to cast our ray is pi over 180, our camera direction, plus the additional camera angle offset. So we're kind of working out a radian, and we're moving it a little bit to work out what direction to cast the ray. We return a cast direction object here, created from our direction in degrees. All this code's online, you can play with it, don't worry. And a little bit more maths that you might have been sleeping through in school happens here. So our cast direction object contains the sine and the cosine of the direction that we provided expressed in radians. Now remember that radians are just what direction on the circle that we're pointing. Now sine and cosine are the 2 main functions used in trigonometry, and they calculate the ratio of sides and of a right angle triangle. So in our case, what they're going to do is they're going to help us work out how far left and right we're going to cast our rays from our starting point. So we're trying to simulate the focal point of a camera. And that's all of it. That's like the whole thing. That's the whole algorithm. Big air quotes algorithm. we loop forwards, walking one step forwards, following the shortest path a ray can take. We do this by using the sine and the cosine along with the current step x and step y values. So we just increment the xy location a little bit each time, which calculates the length that one step forward would be in our simulated 3D world of characters. We compare the length of each step, choosing the shortest path every time. Once we know which it is, we either go one up or one across, or one up or one across. And we're basically jaggeding through our array to find a surface. Inspects then returns a sample point, the thing that it reaches at the end of the steps. And if the next step has no height, we know we can continue onwards. If there is a height, we have to stop. If we're at our max camera depth, we also just give up and return nothing. Now, if we reach something with a height, we found a surface, we store our sample point, and we return our completed traced path, which has a length, the number of steps it had to take, and what it hit. Now, this is a really confusing looking block of code that took me like a week of time to wrap my head around when I first did it. What it does is if you give it an angle in degrees and a pair of coordinates, it calculates what the next step forward along the line would be. We call it with the sine and cosine values that we created when we generated our cast direction object, and like it feels really mathsy and it's an eyeful. But what we're doing is we calculate an x, a next step. We take our cosine value, which is called run here, and if it's greater than 0, we add 1, and if it's less, we subtract 1. It's inverted when we call this method for our y coordinate, and instead of cosine, the sine value becomes our run, and our y has 1 or 0 subtracted to it, and that's kind of how we do that jagged calculation up. We record this change in length, we generate a new coordinate, and that's what we're sampling. Now, if the first value is x, we just return the location. If it's y, we flip our x and y coordinates, and we flip the sine and cosine. There are probably prettier ways to do this. Like I say, I almost lost my mind writing this particular little bit, but as soon as you do it, you just need to inspect the sample point to detect a surface, right? Because you've got the length, you've got a surface. All it does is it shifts either x or y by 1, depending on if x or y was the shortest path. It calls detect surface, which converts our double down to an integer, the x and y location in the original array, and then the surface at function here just checks the character at that location. If it's a wall, returns a surface with a height of 1, otherwise it returns a static nothing. Now, these values are consumed by the loop back in the ray function, which evaluates the response to see if we've collided or not. And in a more comprehensive implementation, you could use different characters in the little weird 2D map format, just like the Wolfenstein 3D map did, to signal different kinds of surfaces. So Wolf 3D had walls, secret walls, doors, and I think there were a couple of pixels and like artifacts they could put on the walls, and that was their whole map format. So this is really like, let's go with it. It's 50% of Wolfenstein 3D, obviously. So after we cast our rays, we have a total distance value for each point on our horizontal axis. We need to do a little bit more work to convert this into an image that might look like something. So I split these two steps out to make them look a little bit more explicable here. We do our cast rays, and then we've got like a bitmap renderer that takes the column data and does something with it. So when we're writing the bitmap, we're just going to write a bit to a memory stream, save it to disk in an image editor, something like that. So I think what I've got under here is there is just a bitmap, and we're just painting pixels for each of the XY coordinates, just filling up, scanning across a bitmap object in C#. So firstly, our image width and image height are 10,024 by 768. So this is a standard if small in 2022 resolution. First, we're creating a new image using the wonderful ImageSharp library. I always like to plug that library. It's one of the best things in C#. We set it to our desired width and height. Now next we're going to loop around each sample point in our column, and the column integer is also the x coordinate. So we do this by taking the height, we multiply it by the height of our surface, so which is either 0 or 1, and that's the maximum number of pixels that we can possibly fill up. Now then we're just dividing it by the distance traveled, so the further we travel, the smaller the height of our pixels becomes. Now we also then divide the distance traveled by 2.5, because otherwise the camera feels like it's really close to these objects. And For all the pixels, we're just going to set a texture of a mucky grey colour. And it looks like that. And it looks like that. And I was kind of surprised how pseudo 3D it looked just with 2 colours in the whole thing. It's a ray traced output. Now, it felt like a really long journey, but the whole of that code sample is less than 200 lines of code, which is vaguely terrifying, really. And you can see the walls projected towards our focal point. You see that the subtle fisheye of us simulating the lens of the camera. And what we can now do is we can update our code to call a new select texture method. And we're going to do some really quite back of the envelope maths here and treat RGB 200, 200, 200 as an off-white as the maximum brightness we're ever going to render. And then the further the distance we are from the camera, we're just going to tweak that RGB color a little bit so things do that. And we get a gradient, right? Just by tweaking that one number. And it's great, and I love it. Now, see this gradient? I love this gradient. This is my favorite gradient. The reason I like this gradient is I made it in 10 minutes in Paint.net, and I used it to simulate a floor and a ceiling just like Wolfenstein 3D did. So I just cheated and didn't bother rendering any of the rest of the thing. And you just stick a picture behind it and it looks real, and that's exactly how they do it in Wolfenstein 3D. It's just a picture box. It's just a picture box in a WinForms app. It's brilliant. It's good enough to play with, right? And I stuck it in a WinForms UI, and I wired up some controls. And every time the control on the WinForms UI was pressed, I just changed the XY position of the camera, and actually this thing in literally 15 minutes gives you a working game. Now there's a little bit of maths in here about the camera location. It's just the same sine and cosine calculation we did before. And at the end of the day, I also crammed it into a Razor Pages app, so you could edit the map in real time, and you hit submit there and it changes the thing and renders it in the browser, which is pretty fun. You know, honestly, I did this mostly to see if it would work. And there are plenty of more places you could take this prototype, right? You could do texture mapping, you could do half-height walls, you could do images, you could do bitmapped 3D enemies and things in there, all using that same kind of coordinate system. Obviously, this code isn't performance optimized, but it's fine. And honestly, the languages that we have today are totally capable of doing less than 200 lines of code, what was really, really hard in like 1995, and that's amazing. If you want to build games in C# today, just use Unity. Oh, honestly, just use Unity. But I hope you could go on these kinds of adventures and see what you can make just by playing with cool things. Now, the code for the sample is available there, possibly, still. I don't know. I'm sure you can Google it. It's on GitHub. You just Google my name. I think I'm actually running out of time. Yeah, so I'm going to go quicker now. There's a thing about it, whether this is the same as ray tracing. The answer is basically sort of. Yes, I spoke about it before. It's what modern graphics cards do, but they add a wrapper of AI around it, and they're bouncing light rather than just drawing single points of projection. And what I really want to do is I want to leave you with a very, very small anecdote about a question I had when I was 10 years old. So I remember trying to play Doom on an underpowered 486 computer in like 1996, because I had a rubbish computer. And it was really choppy and it wouldn't run fast, and one of the options was to reduce the size of the window into like a letterbox format, and the game would run better. Similarly, I also played the weird Doom port on the 32X, and as one of the 7 owners of the 32X for the Mega Drive, it too was rendered in a really smaller window, and I remember thinking to myself, why is it faster when you run it in a letterbox? Well, obviously in writing this talk, and by virtue of that, I realized the reason it was faster is because the small amounts of raycasting they were doing had less pixels to scan, so it was faster. I hope this talk has inspired you to try weird things, just to see if you can build weird stuff. Go write a 3D engine. You're never going to use it, but it doesn't matter because it's fun. And God, we should do more fun things. And if I didn't do things because they were fun, I would have never done this. Don't do fun things. You'll love it. Thank you very much.
Thank you, David. I love it how fast you finished everything when you saw my face
that
looking
was
at
the
you.
get off the stage.
Like, girl, 10 minutes late.
Sorry.
That was
everybody.
long. Yeah, we have a Lithuanian CTO of the Year Awards happening in Alpha, online and on location at the moment, starting now. So if you want to go there, run. And if you have any questions, we can answer, I think, one or two just for fun. But I really doubt it because these awards, you know.
The big awards, go vote for your CTOs.
Mm-hmm.
Said
Somebody
said
online.
nobody ever.
Listen, David, do you know one lone coder?
Not personally.
Not personally? Because Johan on Pine said that some indication says that he is a fan of one lone coder. So
We're just
Google.
interested in the same things.
Google something. Okay, in 10 minutes we will have a session about getting greener, living in a greener world and sustainability using clouds and stuff. But also, yeah, I have to remind you, we have this very important CTO of the Year in Lithuania, of course, awards happening right now in Alpha Stage.